So hello everyone, this is lecture 1 for the quantum mechanics. From today onwards we will start this very interesting topic or subject or the branch of physics which is quantum mechanics. Okay, so there will be 50 to 60 lectures for quantum mechanics and we will move forward with so enthusiasm and with interest, and I will give you details of everything here, and it will be very interesting to learn the quantum mechanics because this is beauty of physics or the space or the universe, you can say. So let's say see first the content we will study. Okay, so in the starting lectures I will go slow, then we will pick up some speed. Okay, so today we will discuss the content, what we gonna study. So first we will study about the development of quantum mechanics, and here development means the historical development, means how we come to this quantum mechanics. Okay, so why and how it started. So in that we will study about the black body radiation, because this was the starting, means when we see that there is a spectrum from a hot body, means any hot body emitting a radiation, means any body which is heated will emit a radiation with a frequency range, and we plotted this curve. So this radiation was called the black body radiations, and at that time these radiations were not explained, means nobody was able to explain these radiations and this curve. Okay, so that's how our quantum mechanics started, and in this we will study about the Wien's displacement law, Stevens law, Rayleigh-Jeans law, Planck's radiation law. So first of all, this Rayleigh and Jeans tried to explain this curve by the classical law, means they consider the wave nature of the radiation and try to explain this, but unfortunately they were failed. Then came the Planck's radiation law, and he explained this curve very efficiently with the quantum, means they consider the radiation as particles. So after when this explained this curve, then it came into the existence the dual nature of radiation, the wave and the particles. And yet there was no experiment to prove this particle nature. First it was this photoelectric effect. Okay, so it was done before, but the real representation or interpretation was done by Einstein after many years. So this is photoelectric effect, Einstein interpretation of photoelectric effect. We will study this. This was the first experiment. Then comes the Compton effect. So that's how we will go in the development of quantum mechanics. So this was the base to develop this. Then we will study about the de Broglie hypothesis and matter waves. So de Broglie means they said that not only the radiation have the dual nature, but every particle of the matter has the dual nature. So that's how we move forward in the quantum mechanics. And they said that every particle like electron, proton or anything will have the wave nature and particle nature both. Then we introduce this de Broglie wavelength, that is h by p. And to support this, there was an accidental experiment done by Davison, German experiment. Means they just accidentally found that there was a diffraction pattern due to electrons. Okay, then it was done properly, and there was this Thomson experiment also. So these experiments prove the particle nature of the electrons and all the matters. Okay, so they got the Nobel Prize for this. Now let's say then after this what we will study. Now let's consider that there are real waves we know about, means there are longitudinal waves, sound waves, EM waves. We know about that in EM waves the electric field and the magnetic field are oscillating. In sound wave we know the pressure of the gas or anything, the surrounding of the medium is changing, and that is pressure is oscillating. So that's how you get the sound wave. So in the real waves we have something oscillating, is E can be written as electric field as E naught E I omega t minus kx. Same B can be written as B naught exponential I omega t minus kx, and this P is pressure equal to P naught for sound wave. So we can represent these real waves in the form of this, means there is something oscillating. But if we are talking about these matter waves, means we are saying that every particle contains these matter, means waves. So what is oscillating in these waves? So this is actually not known till date by anyone, means nobody knows what is oscillating in the matter waves. Okay, so we will understand the mathematical forms, and we will go into the mathematics more of the quantum mechanics, because that is helpful, and we will study all these things which is helpful in the real world. So we will go to the understanding of this oscillation and all things, and we will study about the wave packet and the wave function. And this is wave function actually, because we don't know what is oscillating, so we give this symbol to this wave function, that is psi x. Okay, so this is wave function for matter wave. So we will study wave packet, wave function and all. Then we will see the Max Born interpretation of this wave function. See, if there is something oscillating, that should be oscillating, otherwise it can't be wave. So we consider that this right hand side form will be same for that wave also. So we considered this wave function, and it can be written in this form. So phi x can be written as a exponential I omega t minus kx. So we just introduce this form for the wave function. So this was the Max Born interpretation. Okay, and now see, in the EM waves or any wave, we know intensity is nothing but amplitude square, or in the electric field you have electric field square, and this intensity is nothing but number of photons per unit area per unit time. That's how we represent intensity at any surface. The number of photons per unit area per unit time they are falling, that defines the intensity. So square of this wave function must be representing something, and that should be the particles, means it is also representing the particles, means photons. So this is, if this is the wave function of a matter, so this is the probability. The square of this wave function will represent probability of finding particles. Okay, because here also we are finding photons, so this also represents the probability of finding particles. So that's how we define this, means we don't know the real nature of and what is oscillating and what is what, but we can take the quantitative approach here, which will be helpful for us. So that was the Max Born interpretation. We will go in detail. I am just giving you a simple idea how we will move forward. Then we will study about the validity of wave functions, means means the conditions required, that where it is defined, where it is not defined, and what is conditions should be followed, and wave function should be continuous and differentiable and all. So those conditions we will study here. Wave function is position space. So we will see that, means there are questions in the examinations asked that you have to draw the wave function in the position space or the momentum space. So we will study about them. Then we will see the Heisenberg uncertainty principle, and we will study about the expectation values. Then comes this, means without these two persons, the first one is Schrodinger and second is Heisenberg, quantum mechanics will never be a real thing. Okay, so these two men gives us the quantum mechanics actually. So you know, this is the equation kind, means any wave can be represented using this equation. So if you take for the radiation, if you solve the second order differential equation, you will get this. For electric field, for magnetic field you will get this, and for pressure you will get this, solving this. But you can't use this equation in the matter waves, because this equation is not valid. We will discuss about it, how it's not valid in the matter waves. So if there is electron in a potential well, or it can be a box, and it's a harmonic oscillator, it can be inside this, electron can be inside this, or in a hydrogen atom we have electron. So the waves of these electrons can't be defined using this equation. So there should be some equation which can be defined, which can define these electrons or the matter waves due to these electrons inside these potentials. So these equations was given by the Schrodinger, and we have two kind of Schrodinger equations, that is time dependent and the time independent. So this is the formula. Just introduction, you don't need to remember these yet. Minus h cut squared by 2m, this h cut represented by h upon 2 pi. Del square phi psi plus v psi equal to e psi. So this V is the potential, E is the energy, and psi is your wave function. H is your Planck's constant, M is the mass. So if you solve this equation for this potential of a box, you will get a wave function for this. If you solve for this harmonic oscillator potential, you will get wave function for this kind of system. And if you use potential for a hydrogen atom, you will get the solution for this. And this is time dependent wave equation. Same goes with this also. Minus h cut square divided by 2m del square psi xt divided by dx square del x square plus v, this is potential v, psi xt equal to I h cut del psi by del t. So these we will study about the Schrodinger wave equations here. Then see, we don't know the qualitative idea, means we are not having till date any idea about that what is oscillating and what is quantum and what is means matter wave actually how they are and what is the physical structure and all. So we will study the mathematics, okay, because that will give us everything we need, okay. So we have enough time to think about the physical nature, because but what we need is this mathematics. So let's say we already defined the wave function, the square of wave function, as the probability. So if particle is here, then the wave packet for this particle can be drawn like this, because this is representing the probability. So when there is particle here, then it will be like this, peaking here, and as we are going to the infinity, it is going to 0 here, because this is representing the probability actually. So this kind of wave packet we will get for the free particle. Now see, this wave particle or this wave packet is made up of infinite number of waves, monochromatic waves, okay. So this can be this first wave, second wave, and different frequency, different wavelength. So these all together make this wave packet, okay. These are monochromatic, so we represent them as phi 1, phi 2, phi 3, phi n. So these can be, means this wave packet is a superposition of these waves. So it can be written as psi x as c1 phi 1 plus c2 phi 2 c3 phi 3, where c1 c2 c3 are constants. So phi x can be written as summation of ci phi I x. Now see, these phi 1, phi 2, phi 3, these all are linearly independent to each other. And what is the meaning of that? Means if means they all are perpendicular to each other, and no one function can be related to other one, okay, using any function. You know what is linearly independence, you can see that in the mathematical lecture mine, okay. So in the mathematics of this lecture you can see the how we define the linearly independent, okay. So now if there is this vector r, that is 2 I cap plus I j cap plus 3 k cap, okay. So just an example, see this I cap, j cap, k cap, these all three are orthogonal to each other, and these are the basis vector for a 3D space, and these are perpendicular. So same likewise we have these phi 1, phi 2, phi 3, means these are also representing the basis vectors, and these basis vectors are present in a Hilbert space, means I, j and k are in the real space, that is Euclidean space we define. So where phi 1, phi 2, phi 3 and infinite, they can be any number, okay, and all will be orthogonal to each other. So the space in which these are defined is called the Hilbert space. We will study about it. So just remember this, they act like this I, j, k and l, means these perpendicular vectors in the Hilbert space. So and c1 c2 c3 are like here 2 1 3 and all. So as I j is equal to 0, j k 0, all are perpendicular. So phi 1 dot phi 2 will be 0, phi 2 phi 3 will be 0, phi 1 phi 3 will be 0, all will be perpendicular. So I hope you get the idea what I am trying to convey here, and that's why we treat this wave function as vector, because this is summation of these, and this is a vector because these are the vectors in the Hilbert space, and orthogonal vectors definitely. So we will treat phi x as a vector with phi 1, phi 2, phi 3 as a basis vectors orthogonal to each other, and these are defined in the Hilbert space, complex space we called it. Then we will see some notations how we define these vectors in the Hilbert space. like Dirac notations we call them, means cat and bra notations we will see. Then we will study the properties of vectors, operators and observables. We will see what are operators. Then computational algebra. In operators we will see Hermitian operator, anti-Hermitian operator, projection operator, parity operator, unitary operator. In unitary we will study about the transitional operator, time evolution operator, rotational operator. So we will study all them. These are the tools of quantum mechanics. So up to here our half of quantum mechanics will be completed, up to here. Then start the application part. Before this we will study the postulates of quantum mechanics also. Then the half quantum mechanics is this application part. So we will see this, means there will be some content left. I will tell you in the next lecture. So that's it for today. Thank you.